Okay, welcome along to another blurting video, this time on capacitors. As ever, I think we'll just get out the really straightforward equations to start with. So definition of capacitance is from Q equals CV, or C equals Q over V. So this is measured in farads, and it's the amount of charge a capacitor can store at 1 volt. And then on top of that, we've got the energy stored in a capacitor, which is a half QV, but it's also a half CV squared, which is a half Q squared over C. And that all comes from this little graph. If we plot a graph of Q against V, then the area under that graph has got units of charge, and that area, because it's a triangle, is a half QV. And then we can substitute in by that equation to replace either Q or V to get those two other equations. And you can see here I've drawn a little picture, and then so our electrons want to travel that way around the circuit because they don't like being on that plate. They're all crammed together, repelling each other, they're attracted to the positive charge, and they move round through the resistor. But we just have to remember somewhat awkwardly the current is in the opposite direction, because current goes positive to negative. This place is positive because it's lost electrons. It's got less electrons than it should. And then we start getting into the thorny issue of capacitor discharge. And we have this classic exponential shape. V goes to V over E in RC seconds, and that is called the time constant. So literally, if you multiply the resistance of that the capacitor is charging through by the capacitance, you get this special time in seconds called the time constant. And similarly, Q for a discharging capacitor, Q against T and I against T all form the same curve. That's then all dominated by this equation, V equals V naught e to minus T over RC, which is just a more complicated way of saying the whole thing. And then we can replace V, can become Q, which is I think how it's written on the data sheet, or it can become I. The equation doesn't change. And then we should just remind ourselves what happens with log. So log to the base 10 of 10 to the x is x. So we've just got to remember that, you know, if we take the logs of something where we've got the power in this, that's the same as the base, we can get rid of the exponential. So here we can say V over V naught equals e to the minus T over RC. So we take logs of both sides, log to the base E, which is log to the base E on your calculator is written ln of V over V naught equals minus T over RC. So now we've rearranged that equation, and we can find the time taken to get to a particular voltage, and obviously that would work with current and it would work with charge. And then we've got our charging experiment. Q against time rises exponentially like that and now Q naught, rather confusing, is the final charge. And this is for the capacitor, so the voltage across the capacitor when you're charging it similarly rises. I should draw a circuit diagram in a moment. Against time. And then the two that fall exponentially with time are the voltage across the resistor in the circuit and the current in the circuit, because V is proportional to R. So these are both V or I, V naught e to the minus T over RC. whereas the other two have the equation. So this is, I already know, Q equals Q naught 1 minus e to the minus t over RC, and that's V equals V naught 1 minus e to the minus t over RC. So you should have probably drawn this to start with. So if we have the circuit for this, there's the battery, there's the resistance R, there's the capacitor, and then we might have a switch. And when we close the switch, the current starts to flow. We can just use V equals IR. Well, V is the voltage of the battery to find the initial current. And with time, for the capacitor, its voltage and its charge rise with time. The voltage across the resistor falls with time, because that the voltage across the resistor plus the voltage across the capacitor must equal the voltage of the battery. And similarly, the current in the circuit falls with time as well. So because of all this time-dependent behaviour, we can use capacitors in lots of different timing circuits.